Hello, everybody. We're excited to showcase our progress so far for the Neural Networks project. You might be wondering what our project is. Uh, we want to see how this new type of neural network called neural operators can be used to model partial differential equations. Compared to traditional methods for modeling partial differential equations, these methods struggle sometimes with efficiency and accuracy, especially when the equation itself becomes too complicated. However, we've seen promising results with neural operators. In our initial experiments, we're modeling the heat partial differential equation using a Fourier neural operator. And specifically, we wanted to observe how the model would model heat dissipation over different patterns, such as a checkerboard with different intensities of heat or Gaussian blobs of heat to see how it converges into one specific patch over multiple time steps.
Yeah, and so with that, I'm going to walk through how we generate the ground truth data that we will then send to our models to try and learn. So, what we're learning basically is the temperature evolution through time of, you could think of a plate of metal, right, discretized. What we're doing is going to be, a mesh, an XY mesh. So we impart some initial conditions, some initial heat conditions on it. These are the three that we came up with and that we've been using for the moment. The first one is a series of random Gaussian blobs, right? And so these are just, circular blobs of heat that will imprint on the mesh. We also have a checkerboard, a perturbed checkerboard pattern that's useful for showing how sort of globally the system will tend towards equilibrium, and then spotting noise to show randomness, especially because these are going to be these high frequencies. So we show that because there's going to be much more sharp features, we show this tests that particular thing. When it comes to Fourier neural operators, they probably rely on the frequency, so we want to see if the sharper features are more or less easily detected. So that's why we had that. This is just some of the few options that we had. And then, yeah, so what we do here, generating trajectories, these are the traditional methods of calculating partial differential equations. So what we have here is numerically calculating what's called the Laplacian, which is just basically like the sum of the second spatial derivatives, sort of the dot product of the gradient and the infinitesimal, the differential vector, if you will. But anyway, these are some boundary conditions. This is enforcing the derivative is equal to 0 at the boundaries, and this is stepping it forward. And then, yeah, we wrap it in a PyTorch tensor. These are the first batch of hyperparameters that sort of parameterizes our grid, our x and y steps, our time steps, the number of time steps we take, the number of trajectories we create, up here is capital N, and then T is the number of snapshots that we'll use to create the animations that we'll show you in just a little bit. Alpha is a number that characterizes the diffusivity. It's called the diffusion constant. So it shows how readily the material will spread heat. A higher diffusion constant, if I remember correctly, means it's more diffusive. But I could have that backwards. I have to check on that. And then, yeah, so then we wrap it all up in some tensors and save it. And so now I'm going to pass it to my teammates to talk about the model itself. So, Darwin, it's all you.
Yeah. So basically, like we said, we're trying to model the heat equation, right? So essentially, we're trying to solve the heat equation on a two-dimensional spatial domain with F and O's, right? And essentially what we're trying to do is we're trying to see how heat gets distributed, at each time step or time evolution from the training data that, like John described, that we generate, right? And based on the hyperparameters that's defined in DataGen file, we have 1,000 samples, and then our time step is around 1,000, right? In the animation, it's actually going to be 500, but for the DataGen, it's going to be 1,000, and at least in the DataGen, it's going to be time step of 20, right? So 20 different images, and so essentially, our training set is composed of around 800 data points. And then we also plot the validation loss, right? And it's going to be 100 samples. And then after that, we're going to use the last 100 data points in the data set for actually testing, right? And so here's our data loader. So FNO and modes. So we have 64 hidden channels. And our output channel is defined by T. And yeah. And so what we're using, right, is for our optimizer, we're using Atom W, and we're using a step learning rate. And then finally, right, to actually calculate the loss, we're simply using mean squared error. And so it goes essentially, we're training it for 100 epochs, and yeah, and so that's just pretty simple PyTorch training code, right? And yep, and then we go through and we actually model what it looks like. But yeah, and I can quickly show a few images. So if we go to Epic Final 100, Epic Final 4, right? We can see that it gets pretty good when it comes to predicting the heat model, right? There's a little bit of noise at the end, but at the end of the day, the prediction is mostly on point. And then we can actually show an animation, right? And this code over here shows the animation. So if I show it really quickly, I can show it for a time step of 5. And so this is what it looks like, right? And so here's our loss curve using mean squared error. And then we have more, right? So let's say we want to model time step of 20, right? And so for the most part, this model is pretty accurate. Of course, the time step is going to be 20, right? So it's not. So as time step increases further and further, right, the model tends to drift off a little bit. So we're still looking on how to scale it better. And this, by the way, for context, the animation is also it's using a time interval of 500 compared to 1,000 in try stuff, right? And this is for time step 15, and it mostly gets it correct. Of course, there's a little bit of noise, and we're still trying to solve that. But for the most part, it seems like we're on the right track. Our loss curve is over here for time step of 15, and for each of these, right, we're training a new model to see to see how the model looks, right, for different time steps. And so we're still scaling it and seeing what the ultimate results will be.
Right. So over here in this sort of plot of three GIFs here, we see that this is the initial condition of our sort of heat dissipation, and this is the ground truth here. So this is generated using traditional numerical methods, and this here is generated by the FNO. So as you can see here, very similar results. Obviously, we have a little bit more noise here compared to the ground truth, but of course, these are generally very promising results given how efficient generating this animation is given using the FNO. We also have a couple of other patterns here. And most notably, we also have a Gaussian blob here as well. Again, very similar results, just a little bit of noise, but very promising results overall.